Hello everyone. Today we will be discussing the concept of logistic regression, right? So let me give you an example. So I have an input column experience, right? The CGPA of a student, and I have the data whether he is placed or not. Okay. So let's say the experience is 1 year, 2 year, 1 year, 3 year, 0 year, right? CGPA of a student might be 0.7. It would be 7, 9.1, 8, 6.7, and let's say 9.8 CGPA, right? So the placement could be 1 or 0, like 1 for placed and 0 for not placed, right? This is 1, this is 0, this is 1. So this is a kind of problem where the output or target column is not numerical, or let's say it's a categorical column. Then the problem is then we can solve it using logistic regression, right? So it is a classification problem. So if I draw this on the XY plane, it would look like, so CGPA, and I would draw it like this. Okay, so these are the students who have been placed, and these students are those who have not been placed. Okay, so what I want to do or required to do is draw a line in between those so that whenever a new point comes, I can classify them or predict that will they get placed or not placed. Okay, so let's say I draw this line in between these two groups, and whenever new point comes, I can tell that whether the student will get placed or not, right? So how do I find this line? Let's say the equation of this line is ax plus by plus c is equal to 0. Okay, and I can write it as beta naught plus beta 1 x1 plus beta 2 x2 equal to 0, where beta naught is this c, then ax corresponding to this and by corresponding to this, right? And x1 and x2 will be my CGPA and experience, right? So first of all, we need to understand a concept that when we can say that a point lies over the line. Okay, so if I put some value of x and x1 and x2 such that this equation is satisfied and the result is 0, so I can say that the point lies over the line. Okay, now how do I know whether a point lies on the right side of the line or the left side of the line? This is the right side of the line, and this corresponds to the left side of the line. Okay, so let's discuss this now. If I say beta naught plus beta 1 x1 plus beta 2 x2 is less than 0, okay, then this would imply that the point lies on the left side of the line. On the other hand, if this would have been greater than 0, so if beta naught plus beta 1 x1 plus beta 2 x2 is greater than 0, this implies the point lies on the right side of the line. Okay, so I hope this is clear up to this point. Then next, what we are required is that I have this given problem where I have these points. Okay, and I need to draw a line between these 2 points, also these 2 groups, so that they can be classified from each other, right? So first of all, how do I know that a point is correctly classified or wrongly classified by the line which I have drawn? So we will understand this, right? So let's say I say positive to those who have been placed and negative to those who have not been placed, right? So let's say I have these plus points here. These are just vectors, 2D vectors, right? And those who have not been placed are represented by this color. Okay. Okay, I will replace 1 by negative so that it is more clear. Negative, right? And if I draw this line, how would I know that this point is correctly classified or not? So let's say all the plus points lie on the right side of the line. Okay. Okay, so I will reframe it as I go to this point and I put the value of this, the coordinates of this in my equation of beta naught plus beta 1 x1 plus beta 2 x2, right? And if this is the given equation of this line, and if I put the coordinates of this point in this line and I get it as greater than 0, then it means this point lies on the right side of the line. And if I say this right side is defined to be the side where the plus point should lie, okay, this is the positive side and this is the negative side. Right. So if I put the coordinates of this point in this equation of line and it is greater than 0, then I can say, yes, it is a correct classification. But what if I go to this negative point, put its coordinates in this equation of line, I will get it as greater than 0, right? But what it should have been, it should have been a negative point, that is less than 0. The value should have been less than 0, that this point must have been on the left side of the line, right? So this is my misclassification. Okay. So we have understood how we are getting that if a point is correctly classified or not. If it is a plus point, and its value when we put the coordinates in the equation of the line is greater than 0, okay, is greater than 0, then we can say that yes, it is correctly classified. Similarly, for a negative point, if we put the coordinates of this point in the equation of our line and we get a negative value, right? Then we can say yes, it is a correctly classified point. Otherwise, we will say that no, it is not a correctly classified point, right? Now we will continue this concept. So let's say somehow I have found a line which correctly classifies my points, right? I have these two same diagrams, but the difference between them is that here I draw this classification line, and here I draw this classification line. So how can you tell that which line is better, right? You cannot tell this because both have the accuracy of 100%. But how can we quantify which line is better, right? So this is the problem we are facing. And to solve this, we have a concept of sigmoid function, which will, what it will do is it will tell how much far a point is from the classification line, right? So I will explain it. First of all, let's understand what is sigmoid function. The diagram of sigmoid looks like this. Okay, so this value is 0.5 when x is equal to 0. This is positive 1, and this is 0. And what is this x-axis is? It is the z. And what is it? It is beta naught plus beta 1 x1 plus beta 2 x2. So whatever value we get when we put the coordinates of a point in this line is the z value. And what is y-axis? It is the sigmoid of it. That is sigmoid of z. Okay, so, and the equation of sigmoid is 1 upon 1 plus e raised to the power z. And we know what is it? Z is this value, right? So the special thing about the sigmoid function is that it is never equal to 1 or 0, or I can say it is equal to 0 when z tends to infinity. So sigmoid of z is equal to 0 when z tends to infinity, right? Oh, sorry, it will be 1. And sigmoid of z is equal to 0 when z tends to negative of infinity, right? And what is the 0.5? It is that when when z is equal to 0, the value of this function is 0.5, right? So when we put beta naught plus beta 1 x1 plus beta 2 x2, and if it comes equal to 0, then the sigmoid of z will return a value of 0.5. This is the concept we need to understand till now. And then now we will see how this sigmoid function will help us find the best line for us and differentiate which line is the best among these, right? Okay, so we will move ahead now. Okay, so I will draw a classification problem. Here I have some green points, right? Uh, I have this classification line, and then I have some of these points. Okay, so now if a point lies on this line, right, what will sigmoid return? Sigmoid will return 0.5. Why? Because if a point lies over this line, over our classification line, that is beta naught plus beta 1 x1 plus beta 2 x2, and if a point lies over this line, this equation will give output 0, and sigmoid of 0 is equal to 0.5, right? So we give this value 0.5. Okay, now if I take this point, it is on the right side of the line, right? This is the right side, and we have seen if a point is, if z is greater than 0, we will get a value that is greater than 0.5, right? So let's say this value is equal to 0.6. And since this is even more right to our classification line, we can say that it is equal to 0.8, right? Similarly, a point to the left of the line will return a negative value of z. And when z is equal to negative, that is from this side, it will return a value less than 0.5, but always greater than 0, right? So I can say that this point has a value of 0.4, and this point has a value of 0.3. So because z will be even more smaller for this point, then the sigmoid will return an even small value for this one, right? You can compare it. So if it is -2 and it is -4, so this point will be smaller than this, right? So yeah, we have assigned some numbers to this point, which we will look now. What are these numbers and why are they there? So uh, can we assume these numbers to be the perpendicular distances from this line? We can visually also see that as the distance between a point is increasing, the value is also increasing, right? Which we want. Now, what is happening here that you will see. Okay, so now can we also say these numbers to be probabilities? What probabilities? Let's say if a point is over the line, it has a 50% probability that it is a green point, and it is only 50% probability that it could be a red point. But when we talk about this point, as it is very far from the classification line, we can be very, very sure that yes, it is a green point, right? We are 80% sure here that it is a green point. When we come a little bit near to the line, we can say that we are only 60% sure that it is a green point. When we move toward the left of the line, it is not the probability of red, but it is this is also probability of green point. That we are only 40% sure that it is a green point. This implies we are 60% sure that it is a red point. For this point, we are only 30% sure that it is a green point, and this implies that we are 70% sure that it is a red point. Okay, so I hope you are understanding this point, that these numbers are nothing but probabilities which we are getting with the help of sigmoid function. When z is greater than 0, we get a value greater than 0.5 but less than 1. And when z is less than 0, we get a value in this region that is less than 0.5 but greater than 0. Okay, and these are just probabilities of a point on the right side. That is, in this case, we have a green point that it has a 80% probability that it is a green point. It has 60% probability it is a green point, and it has only 50% probability that it is a green point. Right. So I hope you are understanding this point. And now we'll move how we quantify that how our model is performing. So let's say these are my red points. Okay. And now these are my green points. And this is my regression classification line, right? And the probabilities are 0.7, 0.6, 0.6, 0. This is 0.4, this is 0.3, this is 0.3. And now if I have a misclassification here, but it has also a probability of 0.6, one more classification error, it has a probability of 0.8. I know this is a wrong classification, and our model is saying that it is 80% sure that it is a green point. But we will look how this point will be penalized now when we evaluate or quantify the performance of our model to improve this line, right? Similarly, we can have misclassification on the left side as well. And let's say this is the point, and it has also a probability of 0.3. Okay, so now we will look how we quantify this. Okay, so to quantify, what we do is we go to a point, ask it what is its probability of being that point on this with respect to on which side it is of the line. I will explain. Let's say I go to this point, it is a green point, it is a correct classification, and it has a probability of 0.7. So I write 0.7. Then I multiply it with the next point. I go to this point, I ask what color it is, what is its probability, and where does it lie, or is it a correct classification or not? Yes, it is a correct classification. For this point as well, it is a correct classification, right? It is a green point. Now I go to this point, it is a misclassification, right? So I ask what its probability of being the correct color. So it has a probability of only 20% of being red, right? Now I go to this point, it has only a probability of 40% of being correct, right? Now, if I go to the left side, what is the probability of this point being red? It is 60% because 0.4 is the probability of a green point, right? So it has a probability of 60% of being red. Multiplied by this point, it has a probability of 0.7% of being red. This point has a probability of 0.7 of being red. Multiplied by this is a misclassification, and what is its probability of being green? It is 0.3 only, right? So you will ask how will multiplying these numbers will tell me something which through which I can quantify my model. Okay, so let's take another example. This time we have only 4 points. This, right? This is our green point. This is our green point. This is our model. This should be the green side, and this should be the red side. Okay. Okay, I will increase the number of misclassification then. And here it is green points. Okay. And probabilities associated with these are 0.6, 0.6, 0.7, 0.7, 0.3, 0.3, 0.3, 0.2, right? So now, if I go to this point, what is the probability of being a red point? That is like it is a wrong classification, right? It is a wrong classification. So what is the probability of it being red? It is only 40%. What is the probability of this point being red? Because this given probability is the probability of it being a green point, which it is not. So what is the correct probability? It is 30%. Now I go to this point, the probability of it being correct is 0.3%. And since this is a correct classification, I will multiply it with 0.6. So you will start noticing by now that when the classifications are correct, I am getting a larger number here, right? Only there is a one small number. But when the classifications are getting wrong, the probability is reducing very much. Like this is 0.4, this is small number, this is a small number as well. And if I multiply large numbers, it will give me a large number, right? And if I multiply these small numbers, it will be a smaller number than this model. Isn't it right? So when here I have more number of correct classifications. Here in this case, I have more number of wrong classifications. So when I'm multiplying the probabilities, like right, when I'm multiplying the probabilities, model one will give me a larger probability than the model two, right? So this is what we are required to do. We need to maximize this quantity. If I get a maximum quantity of this, I know that my model is performing better than the rest of the models, right? So this concept is called the concept of likelihood, where I am multiplying the probabilities, right? But here a small problem arises. It is a problem we call underflow. Okay, so this problem of underflow is that if I have decimal numbers like 0 0.1, 0 0.3, 0 0.05, 0.07, and if I multiply them, I will be getting a very, very, very small number, right? And if I have so many decimal places, it becomes sometimes difficult for the computer to maintain the accuracy of its calculations. This is a computer science problem, but we have found a solution for this. So basically what we do is we take simply a log out of these, and log has a if log a is multiplied by b inside log, then it has a property of log a plus log b. Okay, so this is a property of log. So similarly, what happens here is if I multiply these probabilities, log of 0 0.1 into 0 0.3 to 0 0.7 into 0.05, okay, so it will become log of 0 0.1 plus log of 0 0.3 plus log of 0 0.7 plus log of 0.05, right? And remember that till now it is a problem of maximization, right? Because we want to maximize this likelihood value, which will imply that yes, we have most of the correct classification 7-number model, right? But what if I simply take a negative out of this model, or let's say I introduce a negative sign, then it will become log of 0 0.1 plus log of 0 0.3 plus log of 0 0.7 plus log of 0.05, right? And now this has become a problem of minimization. If I have a positive number, then I will be maximizing it. But if I take a negative out of it or introduce a negative sign, let's say, then it will become a problem of minimization, right? Yeah. So we are trying to do that. And this function is called as log likelihood. What are we doing is minimizing the log likelihood function. So how would I write it mathematically? Let's look at. So it will be yi multiplied by log of yi hat. Right? Is this right? So what is this? This is the probability. And this is the point. So let's say if this point is 1, yi is the actual data point. If it is 1, then it is log of the probability of it being 1, right? So it is 0 0.1 plus 1 into log of 0 0.3. But there is a catch in this formula. What if my actual point is 0? Then if this point goes here, the whole term will become 0 and it will be plus 0, which is not something we desire, right? We want the probability of 0 as well. So what we do is we change this formula to, and summation will lie here for I equals to 1 to n, that is n data points in which in our data. So it is equals to n I raised to I equals to 1 to n. Then it is yi log yi hat plus 1 minus yi log 1 minus yi hat, right? So this is our log likelihood function, which we want to minimize. And why minimize? Because we are introducing a negative sign out of it. We could have maximized it as well, but computationally, and since we have the habit of minimizing our loss function various times in machine learning, we are taking a negative sign and we are minimizing this loss function. This loss function is also called as binary cross entropy. This loss function, mind that, is only used when we have a classification problem where we have only two categories, like binary classification it is known as, like 1 and 0, male and female in our target column. Then this function is used, and we need to minimize it. And why do we want to minimize it? To get the best line which can classify, which can act as a classification line for our data set, right? So now we will look how are we going to minimize it, and you will be wondering how minimizing this line or this equation will affect our line. Okay, we cannot see any component of slope or intercept in this equation. So how will this affect our like classification line? But if you notice carefully, what is yi hat? Yi hat is nothing but the prediction or the probability of that point being green, or the correct point, like what is the probability of it being green, or what is the probability of it being like right. It's like, oh, yi is the probability of being it green, and 1 minus yi hat is its probability of a point being red, right? If the point is red, actually red. So yeah, we were doing yeah. So this is the prediction or the probability. And how are we achieving it? It is coming to sigmoid of z, and then what is z? It is beta naught plus beta 1 x1 plus beta 2 x2. So by minimizing our loss function, we are finding the value of beta naught, beta 1, and beta 2, which will minimize our loss, right? So this is the case. And now we will focus on minimizing this loss function. So now we have got our loss function. And what are we supposed to find is the optimum value of beta naught plus beta 1, x1 plus beta 2, x2. And we need to find the optimum values of beta 1, beta naught, and beta 2, which minimize this loss, right? And to minimize this loss, we will use the strategy of gradient descent. I hope you know what is gradient descent. Otherwise, I will be soon uploading a video related to gradient descent, or you can look it out on YouTube. Many videos are available related to gradient descent, right? Okay. So what we do in gradient descent is, if we need to update our beta 1, what we will do, we will take our old beta and subtract learning rate multiplied by del L by del beta 1. So that is, we subtract the slope at that point from the actual value to get the updated value of our variable, right? This is new, this is old, and this is slope at that point with respect to beta 1. Okay, so let's try to calculate the value. What will beta 1? So let's try to calculate this value, right, for our update rule. So what is del L by del beta 1? And mind it, what is yi at? This is nothing but the sigmoid of z, and z is beta naught plus beta 1 x1 plus beta 2 x2. I have explained this earlier in detail, right? So I can write it as, let me clear some space. Yeah, so I can write it as negative sigmoid yi log sigmoid of beta naught plus beta 1 x1 plus beta 2 x2, right? Then I can write plus 1 minus yi multiplied by log of 1 minus sigmoid of beta naught plus beta 1 x1 plus beta 2 x2, right? And this is the derivative with respect to beta 1, since I am trying to find this value for my update rule in gradient descent, right? So if I proceed with the derivative, it will be minus sigmoid yi, and log of x is 1 by x, so it will become 1 upon sigmoid of z. And when I enter this, so mind it, sigmoid of a derivative of sigmoid of x with respect to s, x is nothing but sigmoid of x plus 1 minus sigmoid of x. Okay. Yeah, so it is not plus, it is multiply, right? So it will become multiplied by sigmoid of z into 1 minus sigmoid of z, right? And when I enter this bracket, I'm derivating with respect to beta 1. So this term will become 0, this term will become 0, and I will be left with x1, right? Now I add this plus sign, and then I move ahead. It will be 1 minus yi multiplied by 1 upon sigmoid of z. Um, and then I move into this bracket. This term will become 0. Then negative 1 multiplied by derivative of sigmoid of this, and it will become sigmoid of z into sigmoid of, multiplied by 1 minus sigmoid of z. And when I move inside this bracket, we will be left with x1, right? So this is del L by del beta 1. Um, and we can further simplify this. This term will cancel out. Similarly, these two terms will cancel out. And no, this will not cancel out. It should be 1 minus sigmoid of z, which comes from here. Right, log of x is 1 upon x. So this is, and these two terms will cancel out. So I can write it as negative summation. And let's say I don't need summation since I am assuming that there is only one data point in my uh, like data set. Okay, so I have only 1 point, so I don't need this summation. So it will become yi multiplied by 1 minus sigmoid of z into x1 plus, or this negative sign will come out, and okay, let's keep it for now, negative, uh, negative 1 minus yi multiplied by sigmoid of z into x1, right? I can further simplify it. This will become negative of yi minus yi sigmoid of z, and xi could be multiplied, x1 can be multiplied both sides, minus this term multiplied with this, so sigmoid of z into x1, uh, sigmoid of z and this is negative yi sigmoid of z x1, right? This is, if I send the negative sign inside, minus x1 yi plus x1 yi sigmoid of z. There's this minus and minus plus sigmoid of z minus yi sigmoid of z x1. So these two terms will cancel out, and I will be left with negative x1. I guess I'm missing x1 term somewhere. Let me just cross check it. It will be, uh, yeah, it will be x1 here as well. This x1 will be here as well. So minus x1 yi plus sigmoid of z x1. And what is sigmoid of z? It is yi hat, right? So it will become yi hat x1 minus x1 yi. And if I take x1 common, it will become yi hat minus yi. And yeah, this is our result. And I can remove the I as well because we were considering it only to be a single point. So to predict this point, or to update my beta 1, beta 1 is equal to beta 1 minus learning rate, this value, that is x1 y hat minus y. Okay, so this is my derivative of loss function with respect to beta 1 to get my update rule, right? And I can write it as del L by del beta, del beta j is equal to summation yi hat minus yi multiplied by x I j. And let me explain what is I j. Okay, so I is the ith row, and what is j? J is the jth column. Or yeah, so if like I have beta 1, I am calculating beta 1, so it will come from my column number 1, x1, right? And if I'm calculating beta 2, so this j value will have, I'm sorry, yeah. So if I'm calculating for like beta 2, it will consider all the rows from second column. So j will be 2, xi2, right? So yeah, this is our final result. Uh, Let me again clearly write it. The rule for updation would be summation yi hat minus yi multiplied by xij. And yeah, this is it. This is our complete like mathematical background of logistic regression, how it works. And similarly, we will update the value of beta naught and beta 2 as well to find the optimum line that has the minimum that has the minimum loss, right? And we will run this, we will keep updating it until the number of epochs which we have said. Epochs is the number of iteration, which for how many times we will be repeating this process. Okay. And if you know gradient descent, we will reach this point where the loss is minimum, right? And this axis is loss, and this is the value of beta j. Okay. So thank you so much. We will meet in the next part of this playlist, which will be handling like columns with more than two categories, multivariable problem, multivariate classification problem, in which we will cover two things. One is how is softmax used. Second is OVR approach. We will discuss both of these in detail. Thank you so much.